All right, so last time we left off talking about Q learning and Q tables. So to start off today, I'd like you to take a minute or two, turn to the person next to you and see if you can explain this Q function update rule. All right. Who wants to take a shot at explaining this Q function update rule? Yeah, Jared. Here, let me give you this.
So this function's a way to determine how much of a difference we have between what is currently in our Q table that we're trying to learn and what we actually experience given a certain movement. So starting kind of in the middle, R is the reward we actually received for taking a random movement. Plus we add a little bit, and that's the estimated reward for in the future. Gamma max at some future movement. Q of SA, that is what the table says we should have gotten, which is not going to match as we're learning. So you're going to get some difference between what we think we're getting and what we actually got. And with some learning rate alpha, we can then update the table as we go to learn.
Great. So, and then in that right side of the formula, what would you say is the target versus our current, our target Q value versus our current Q value?
If I understand the question right, I think Q of SA would be our current value, and then R plus gamma max, all that would be our target.
Exactly. Yeah, so to reiterate that a little bit, basically what we're aiming for is our current observed reward R plus our estimated future reward after R, and we're using that to predict the value of our current time step followed by all future time steps. I'll try explaining this one more different way, and then we'll take any questions. So another way you can see this is you can look at this as our estimate for R is given by our estimate for values of the future. So okay, for starters, we're taking action A out of state S, and so our estimate for R at this time step could be given by our predicted value for this state plus our predicted value for the next state. And so the difference between those two predicted values would be an estimate for R, and with R as our target. So that's kind of another way you can think of this update rule. Yeah, question. Yeah, so I use target because in once this becomes a deep learning version of this algorithm, then this R plus gamma max is going to be our target that we will take a loss between that target and our predicted value. And so that's why I'm using that language. In this case, we don't have a neural network anywhere in this formula. But yeah, I'm using that kind of language so that when we see this in the deep learning context, you'll recognize this term, this R plus gamma max, as the target that we're training our network to replicate. Yeah, question. Yeah, so you said we can choose R to shape the behavior of the system. And I would say kind of yes, but usually R is given by our environment. And so in a way, like we're designing our environment in a certain way to give us rewards. And then, yeah, and then we learn Q values based on that. Yeah, Jaden.
So once we're outside of training time, is formula for moving.
Yep, exactly. So that's a good question. So once our Q table is updated and learned, then yes, our rule is taking the maximum value action from a given state. Yep, and that's the whole point of learning this Q table. Yeah, question. Why do we have alpha? So alpha is, you can think of it as a learning rate. So whereas gamma is a discount rate for future rewards, alpha is basically a learning rate that says how quickly we update our Q table. Good question. Yeah, question. Why in future learn? So are you talking about inside the brackets? You're asking why we subtract the current value? Yeah, so basically so this provides our current value, so this current value is a current prediction for the value of a state action pair. I'm trying to think of the best way to explain this. So the right side of this equation is basically gives us a difference in experienced reward versus predicted reward. And so we will update our current Q of SA by adding some learning rate times the change in reward compared to what we expected it to be. And so we have both a Q of SA outside the brackets, because that is our current expected reward, and then the inside the brackets is a correction of what we experienced compared to what we expected. Okay, so we did a couple of examples where we put actual numbers into this Q table update function, and we found new Q values. But it turns out that as we manipulate some of these constants, we can learn different solutions for our Q table. So we're going to take a look at this. So if we follow this rule that we just followed with gamma equals 0.9, I think is what we chose. And actually, I can't remember if we chose alpha or gamma to be 0.9. I think we picked alpha to be 1 and gamma to be 0.9. And we update the entire Q table. And then we follow that algorithm that Jaden proposed, where we take the maximum value from each state, the maximum value action from each state. This is the solution. If we're in state 1, our maximum value action is going right with a value of 24. So the arrow points to the right. If we're in state 2, the maximum value action is going right with value 27. So we go to the right, and so on. And you can see that this kind of, if we fill in this entire grid, you can see basically dynamics that will lead us to our solution pretty reliably. However, this was dependent upon some of the choices that we made. So if we make the walls scarier, if instead of giving ourselves a penalty of -1 for going outside our grid and make it, I think -2 is what this is calculated with, we get a slightly different solution where you saw before in the top right corner, we could go either to the left or down. Now it's saying just go to the left. Let's see. Yeah, so before it said go to the left or down, now it's saying go down. So, and that's just by virtue of having this queue update rule leads us to different solutions based on different environment values. This is a change where we change the learning rate, alpha, to learn faster. And you can see that we kind of get stuck in some local minima where it says the maximum value out of state 3 is to do nothing, when obviously we would like to get to our eventual palm tree. And yeah, even in this state, it's in state 8, it's telling us to either stay in place or move away from the palm tree. So you need to tune. The moral of the story is tune your hyperparameters. This is making the future less important. So which parameter controls how much we value future rewards? Gamma. Yep. And so if we're making the future less important, will we make gamma bigger or smaller? Smaller. Yeah, so a smaller gamma discounts future rewards more. Okay, any questions on some of these examples where we change the hyperparameters? Yeah.
In this clear one, fill it back.
Yeah, so the question is, will we, in this particular example, will we end up getting to the goal? If we look at the Q table on the left, I would say the answer depends on what our policy is. If our policy is to take the maximum value action, well, we have multiple equally valuable options. And so if we pick randomly out of those, I'm guessing we're going to eventually get to our goal. But there is a possibility that we start in this left corner and we just stay there forever because we continue taking the no op, the no moving action. So yeah, this one would not necessarily get you to your goal. Okay. So yeah, some theoretic guarantees of Q learning. It will converge if the environment is stationary, and meaning that the rewards don't change. And if we visit every state and action pair infinitely often. Obviously, that doesn't happen in practice, but these are theoretical guarantees. But someone asked this question: what if our action space is continuous? How do you make a Q table with a continuous action space? That means there are infinite possible actions. Well, we are going to introduce something called a Q network. And same deal for states. We can't make a table with infinity columns. And so we're going to introduce a Q network, which will map from states to actions. And this leads us to deep Q learning. We are going to introduce a neural network into this algorithm. So whereas before we would take a state action pair, discrete state, discrete action pair, use it to index into our Q table, and that would give us a Q value of that state action pair. Now we are going to take only a state as input to what we will call a deep Q neural network, and it will predict values of each of our different actions. So this is a diagram of the network architecture. So In this case, our state space is continuous. In fact, it is pixels on a computer screen. This is some Atari game. I'm not sure which one. And we're going to pass it. So obviously, this is a state space that is far too large to create a Q table for. So we're going to pass it through a neural network, a convolutional neural network, and then predict a vector of action values. So no input, up, down, or up, we'll call it north, northeast, east, southeast, south, etc. And then all of those plus a button. So this is our DQN algorithm. And it should look very familiar compared to what we were looking at for Q learning. So we start by initializing a replay memory D. So this is important. The replay memory refers to how we gather experience. We can either gather experience online, where we are continuously interacting with the environment, or offline, where we interact with the environment for a given amount of time, gather experience, and then learn off of that experience without interacting with the environment. Yeah, so we'll initialize a Q network, and then we'll also initialize a Q network Q hat, which will just be a copy of Q with its weights at its previous time step. So at time step 0, Q and Q hat will be the same, but in the future, Q will be basically a version that Q hat will be a version of Q that lags behind Q for one training step. Okay, so then we're going to initialize what we will call M episodes. So each episode is an interaction with the environment. And we're going to initialize a sequence S1 of state action pairs and a preprocessed version of that phi1. You can think of phi1 and S1 as basically being the same thing. Phi1 is just some feature extractor. Okay, so then for capital T time steps, we are going to, with probability epsilon, select a random action. Otherwise, select the argmax over A of Q of our Q function. So can someone explain what they understand in plain English of what's happening at this step with our random versus argmax? Yeah. Exactly. Yeah. So we're trying to introduce some stochasticity in our actions. So yeah. So some of the time we're going to take a random action. The other time we're going to take the maximum value action. Then we will execute that action in the simulator, observe a reward and a new image, or we could call this a new state. And we will set. Well, yeah. We'll call this an image. And then we will say, we will set st plus 1. So we will make a tuple of st, the previous state, the current action, and the next observed frame, and yeah, apply some preprocessing function. And then we will store this, we will call this a transition. So where we have a previous state, phi t, an action, a reward, and the next state. And we will call that a transition. And we'll store that in our replay memory D. Then we will sample a random mini batch of transitions. So just take a batch of transitions from D. And then we are going to, yeah, we will let our reward be either this reward, which you should recognize from Q learning, R plus gamma max over A, etc. Or we will take just RJ if RJ is the last, if the episode terminates. For example, if you win or lose the game. Any questions on this? This is just kind of a technicality dealing with finishing the game. Yeah, any questions on YJ? Yeah. Yeah, so if you didn't actually end, first of all, yeah, in that case, we would observe a next state that is not a terminal state. So we would go to the bottom fork of this action. Yeah. Yeah, this would still work if you never terminate, as long as you're collecting rewards. Yeah, so okay, now we have yj, which is our target reward. And we will perform a gradient descent step on yj minus q of phi j alpha j, phi j our state, aj our action, and theta our current parameters. And so that's just mean squared error between our predicted value of this state action pair and the observed value of that state action pair. And then also note that we used q hat in this when we were calculating yj. So q hat is the frozen version of our q network. And so what that does is it makes it so that we don't have two copies of a network to optimize here. Basically, it says what this makes it is so that when we take a gradient descent step on yj minus q, it will update the q function for our current state instead of the q function for our future state. And then every certain number of steps, we will take a frozen version of q and call that q hat. And that is our deep Q learning algorithm. What questions do you have? Okay, yeah. Good question. Yeah, so epsilon decays over time. So remember that epsilon is a balancing factor between exploration, random actions, and exploitation, taking the argmax action. So with that in mind, can you think why you would want to decay epsilon over time? Exactly, yeah. So hopefully Q is getting better as we're going on. And so we want to trust this argmax, this Q function more, and take the argmax action from Q more often as training continues. Whereas at the beginning of the training, there's no real benefit to taking the argmax action. We should probably just take a random action. Good question. Yeah, what other questions on deep Q learning? Yeah. What is the reason why we reset our target every few steps? So you're talking about Q hat. So the reason is because we want a fairly accurate estimate of the value of our next state. And so if we never update Q hat, then Q hat's going to be left with the parameter, basically the original parameters of Q, which is not very helpful. Does that answer your question? Yeah. Yeah. So basically, we use an old version of Q as an estimate for the value of our future state. Okay. Yeah, Max. Good question. Yeah. So Q so the question is about continuous action space. So in this case, Q is a neural network, and it took as input a continuous valued input, in this case pixel values. So that deals with a continuous state space example, and then it predicted values for different actions. But in this case, it was discrete actions. So is your question how would you handle continuous actions? Yeah. Totally. Yeah, so good question. So in this case, the case that we looked at, the Atari example, there were only about 15 different actions, right? But what if like you have, and actually in most video games, if you think about it, it is a discrete action space. But let's think about the continuous action space example. So if we were trying to predict a single continuously valued action, that wouldn't really work with this current setup, and at least not in a way I can think of. What I would probably do is I would provide the action as input to the network, and then predict the value of the state action pair as the output. So I actually don't know. This is not my field of expertise. I don't know how they handle continuous actions, but probably what I would do is I would provide it as input to the network, and then just predict the value of that state action pair. And then we can use that predicted value Q of SA in our loss function. Would you have to do that for every state action pair? Well, what you would do is you would just get your state and action pairs from your environment, or from your interaction with the simulator. And yeah, I'm not sure I understand your question. Okay, cool. Yeah, question. Exactly. We don't know. We don't have a true target value. The only real signal that we have is in this RJ. And so because we want, like, you can think of a variant of this where we just try to predict the reward for the current time step. And in that case, our target would be RJ, and then we would have an R function of state and action. And in that case, we wouldn't have to have an approximation like Q hat because we're just predicting the next time step. But if you think about it, just being able to predict the next reward is not nearly as valuable as being able to predict the entire sum, like discounted sum of rewards for the entire rest of your experience. And so we want to be able to predict the value of our current state, because like that gives us a lot more information about taking actions than just knowing the value of the next time step. So because we want to know the value of our current state, like expected over like the rest of our rollout, we want to be able to reason about that. And so for that reason, we have to introduce this Q hat to account for the part of the rollout that we don't observe. So we observe RJ, we don't observe the rest of our rollout, which is approximated by Q hat. Yeah, Drake. Correct. Good question. So the question is, what are we subtracting from Yj if Q is a vector? And it actually turns out that Q takes as input phi j and spits out a vector of actions, and then we take the jth action. And so that takes out a single element from that predicted action vector, and that we take the difference between, yeah, that number out of our entire action vector, take the difference between that and our Yj. Okay. Feeling a little better about Q learning? Day 2, taking a look at it. Can I see like a thumbs down, thumb middle, thumbs up about how you're feeling about Q learning? All right. Seeing a lot of to the side, a few up, a few kind of down, but I think we'll take that for now. Hopefully, as you work on the lab this week, it will become more concrete. Yeah. a simpler version and this algorithm. Oh, a side by side of the original Q table. Yeah, the Q table versus the deep Q learning. Yeah, I mean, we can just go back to this right now. Actually, I think it would be a good thing to solidify. So, yeah, in review, for when we are using our Q table, we would take a state action pair and use that to get an index in our Q table, which would give us the Q value of that state action pair. With the deep Q network, we take as input a state and we predict Q values for each action. Now you could think of a variant of this, which we were talking about with Max a couple minutes ago, where we take, if we want to handle, because this setup is for discrete action space, we wanted to handle continuous action space, then we could provide an action as input to the deep Q network along with a state and try to predict a Q value for that pair. Yeah, so there are a couple of variants of how you could do this, but in the case of like the Atari environment where we have a discrete action space, we're going to use this setup where we have a state as input and a certain number of actions as output. All right. So just to see how well how well does this algorithm work? Well, on the x-axis, we have different games, and also these on the x-axis is a comparison relative to human performance. So games on the left of this vertical line, DQN outperforms humans, and for games on the right side of this line, DQN underperforms humans. So things that it's really good at: video pinball, boxing, breakout, Star Gunner. I don't know how many of these are familiar to you. I know breakout. That's the one where you have the little bouncing ball and your I guess paddle. So fairly simple games on the left side. And then on the right side, we have games. The hardest one is kind of notorious. It's called Montezuma's Revenge. Has anyone ever played Montezuma's Revenge on Atari? So Montezuma's Revenge is kind of a dungeon crawling type of game with very sparse reward signals. Basically, I mean, you can think kind of similar to Mario, like you're navigating through an environment and you don't get a reward until you get to the very end of that environment. And so you can imagine, yeah, trying to learn by taking random actions to get to the end is going to be very difficult. So that's a particular challenge that DQN is not very good at. And there have been other reinforcement learning algorithms to try to address that problem of really sparse rewards. Okay. Yeah, there are a couple of other DQN variants which we're going to leave off. You can take a look at the slides if you're interested, because we would like to get to PPO, the other algorithm that you'll be looking at for your lab this Saturday. Okay, so we've been talking about Q learning, which is where we are taking as input a state and trying to predict the values of actions from that state. Now we're going to be talking about policy-based learning, which is similar, but rather than trying to predict the value of a state action pair, we are just trying to predict the most valuable action to take. So it takes the same inputs and the same outputs as Q network, but we're going to interpret the results a little bit differently. So just a couple of terms for background on policy learning. So there's on-policy learning and off-policy learning. So on-policy learning is where the agent picks our actions, and we always follow the policy of our agent. So for example, in our DQN algorithm, we were taking a random action some of the time. That taking a random action would be considered off-policy. Yeah, and then off-policy is where actions are not chosen according to the maximum value action from the agent. And often off-policy learning is used to gather experience with exploration. And then when we actually use the model, we will exploit what we've learned. Here's another term, online versus offline reinforcement learning. So in online reinforcement learning, we have direct interaction with our environment. So our agent can pick the action, and our experience is not stored. It's just used for a single training step. Offline reinforcement learning is our agent doesn't choose our actions, and we learn from recorded sessions, and we can reuse stored experiences. And those sessions are often called like a replay buffer. Okay, so this is the architecture that we'll be looking at for the PPO algorithm. Yeah, question. Totally. Yeah, great question. Yeah, so if you're for offline learning, you could train, like your training sessions could be from you playing the game, which is a really good idea if you want to kind of initialize the network with helpful, like kind of a helpful initialization. Would that be on policy or off policy? It would be off policy, right? Because it would be your policy and not the agent's policy. Good question. Okay. Yeah. So the PPO algorithm, we're going to have two networks. One we will call our actor, and one we will call our critic. Our actor will take as input a state and a predicted value from the critic, and predict an action that we should take. Our critic will take as input a reward from the previous time step, a current state, and predict values of different actions for the actor. Yeah, and so we will have what we will call a value function, which is very similar to deep Q learning, and a policy network, which we will call our actor. And also, whenever you see pi is usually refers to, we call it a policy, and it's usually a probability distribution over actions. Okay, so this is our policy gradient objective function. So we have a couple of parts here. We have a policy network, pi, parameterized by theta, which takes as input a state and predicts an action, and gives us a value, basically, yeah, predicts which action we will take. We also, and then we're going to take the log of that policy, and we're going to take the dot product of that with what we'll call our advantage vector. And that advantage vector is going to be an estimate of the relative value of an action relative to other actions. So, and that advantage, predicted advantage, will be provided by our value network. And so the advantage function will be given by the experienced reward minus the predicted value of your given state. And so this is going to be a little bit different from Q learning. So in Q learning, RT was the reward for a single time step. In the PPO algorithm, we are going to basically take entire rollouts in our environment, and RT will be the discounted sum of rewards given a rollout. And so before, with Q learning, you remember we took Q hat, which predicted the value of our future state. We don't have any Q hat here. We just roll out all the way to the end of an experience, whether that's a given number of time steps or whether that's until the environment terminates. And so, yeah, in this case, our capital RT is a sum of discounted rewards, but each of these R sub T's is observed from our environment. And so this is kind of the intuition behind this algorithm. If the advantage is positive, then the gradient of our loss will be positive, and we will increase the likelihood of that given action. If the advantage is negative, then we will decrease the probability of that action. Do you feel like you understand this idea of advantage and what it's telling us? Think about it for a second. What is this advantage telling us, and how is the advantage, like how does capital R sub T and V fit into our advantage? Yeah, Sam? Exactly. Yeah, I think that's a good way of putting it. It's our improvement from choosing. Well, sorry, let me make sure I'm precise about this. Yeah, it's our improvement given a certain action over basically the average expected value over all actions. So, yeah. And so basically it says that if a given action is likely to lead to a higher value than what our value network is saying is the value of our current state, then we're going to make that action more likely. Exactly. Okay, so this is our algorithm. We're going to initialize our policy network and our value network. And we are going to collect a set of trajectories in our environment by executing the current policy. So on policy learning. At each time step in each trajectory, we're going to calculate our current R sub T, which is the discounted sum of rewards up to this point. So yeah, and then, or actually, sorry, the discounted sum of rewards starting backwards up to this point. Does that make sense? So we'll start with the reward for our last action, and say we'll take gamma times that reward, and then we will add the reward for the previous action, and say gamma times that, or well, so it'll be gamma to the k times the last reward plus gamma to the k minus 1 times the previous reward, all the way till we get back to our current time step, t, lowercase t. Then we will calculate the advantage function, the difference between our observed discounted sum of rewards and our predicted value of that state. And then we will update, so that then we have two different updates. We're calling our baseline is our value network. So we're going to optimize our value network by taking the mean squared error between the expected value of the state and the true value of that state. And then we're going to update our policy by basically updating actions that give higher advantage to have higher likelihood, and actions that have lower advantage to have lower likelihood. And then we repeat that. So we then, yeah, get more experience, update the value network, update the policy network. And yeah, each of these updates for the value network and the policy network, these themselves are loops over like optimization loops. And so these are not single time step updates. These are, we're going to fit our value network, then fit our policy network before we gather more information. Okay, and then honestly, we are almost there to the PPO algorithm. We're just going to clip our loss in a specific way that gives us that helps to kind of regularize our network, but this is basically the algorithm. Any questions on the policy gradient algorithm? Yeah, Brendan. We fit the pi sub theta, which is a network, which is a neural network. Yep, the log pi times the advantage is only used for updating the policy.